This is a derivation of the minimum curve radius given the design speed, banking angle, and coefficient of friction. So I've got a vehicle that's traveling at a design speed v along the slope that's super elevated at an angle theta. Let's examine the native forces. You've got the centrifugal force that is trying to take this vehicle up the slope or slide it up the slope, and that would be mv square over r. The normal reaction force is, let's say, given by Fn, the weight of the vehicle mg, and the friction force Fr. I've defined the coordinate axis. X is along the slope and y is perpendicular to it. Now let's take resolve components of the centrifugal force and the weight in the x and y axes. So the components of the centrifugal force, knowing that this angle is equal to the banking angle, would be mv square over r times cosine theta. The other component would be the sine component. Similarly, for the weight of the vehicle, knowing that this is the angle theta, which is equal to the banking angle, the component along the x direction would be mg sine theta, and the y direction component would be mg cos theta. Now we're going to use simple force equilibrium in the x and y directions. Let's start with the y direction. So force balance in y direction. So for that, the normal force Fn would be equal to the component from weight plus the component from the centrifugal force. First equation. Let's write the expression for the friction force. Fr is equal to coefficient of friction times the normal force. That is second. We know that the friction force is going to assist us and prevent sliding. So let's plug into the friction force the value of Fn from equation 1. You get Fr is equal to Fs times mg cosine theta plus mv square over r times sine theta. Now, notice that the centrifugal force is assisting you in resisting itself. So this is the part that's ignored by the codes conservatively. And the expression for the friction force that you're allowed to use is Fs times mg cos theta. Okay, now we'll do the force balance in the x direction. So the resisting side would be the weight of the vehicle, mg sine theta, plus the friction force Fr, which would be Fs times mg cos theta, this force and the friction force, and that should be greater than equal to the force that's trying to slide the vehicle, or the component coming from the centrifugal force. On the left hand side, I'm just going to take mg cosine theta out common, and what's left inside is tan theta plus coefficient of friction. This should be greater than equal to mv square over r cosine theta. We can cancel out cosine theta and the mass on either side. And if we take r to the left hand side and rearrange things to isolate r, we get r should be greater than equal to v square over g, 1 divided by tan theta plus fs. And of course, if r has to be greater than equal to that expression, we can also say that that is the minimum value of the radius of curvature as a function of the design speed, banking angle, and coefficient of friction.